In this video, we're going to talk about applications of function models. We're going to talk about an activity about bald eagles and how they nearly went extinct. And we're going to try to create a function model that best fits this data and answer some applicable questions. So here's our scenario. It's from the Bald Eagle Soaring Back from Near Extinction article that was published in a mathematical journal. So here's our scenario. It was estimated that in 1963, there were as few as 487 nesting pairs of bald eagles in the lower 48 states. These numbers are low when taken into consideration that when the bald eagle was made the nation's symbol in 1782, the U.S. Fish and Wildlife Service estimates there were as nearly as 100,000 nesting pairs in this region of the United States. What caused the decline of the eagle? Initially, the cause of the decline was the competition of food with the increasing migration of European settlers. Following World War II, DDT was commonly used as a pesticide to control mosquitoes and other insects. Unintentionally, it was washed into nearby waterways, contaminating the bald eagle's primary food source, fish. At Protection of the Endangered Species Act, the bald eagle has made a recovery leading to a removal from the endangered species list in 2007. The following activity is designed for you to work with a partner to do some internet research and to determine a curve of best fit using the data provided. So this table here provides all the data from that was found in the United States Fish and Wildlife Service's website of all the nesting pairs from 1963 all the way to 2006. So we see in 1963 there are 487 pairs, and we see even as recent as 2006 there was 9,789 pairs. So the bald eagle has made a remarkable recovery from nearly being extinct, and that's ironic because that's our nation's symbol. So let's answer some questions. Why do you suppose the U.S. Fish and Wildlife Service do not have any data after 2006 for the bald eagle? So this is a simple question. So I would say the reason they probably don't have any data after 2006 is because after 2006, it says somewhere in the article that is removed from their endangered species list. Removed from endangered species list. Number 2, identify the variables, which is the independent, which was the dependent. So we look at our variables. Let's write this down. We'll write independent variable. And our dependent variable. Our independent variable is going to be the year. And our dependent variable is going to be our nesting pairs. Okay, we're going to pause for a second and we're going to try to create a scatter plot of this data using Desmos. Okay, from here, we're going to enter our data into a table on Desmos. So to create this table, what we need to do is hit the plus sign and then hit table. And X1, we're going to enter our year. So we're going to do 1963, 1974, 1981, 1984, 1986, 1987. Let's see if we can. 1988, 1989, 1990, 1991, 1992, 1993, 1994, 1995, 1996, 1997, 1998, 1999, 2000, 2005, and 2006. And Y1, we're going to enter all of our pairs. So our first pair was 487, then 791, 1188, 1757, 1875, 2238, 2475, 2680, 3035, 3399, 3749, 4015, 4449, 4712, 5094, 5295, 5748. Let's fix that. 5748, not 5448. 6404. 6471. 7066. And then 9789. Take note, we can't see it, so we're going to hit the magnifying glass, and now we can see all of our data points. If we click one, we can see that's 1963, 487, and the last point would be 2006, 9789. So there is our scatter plot. Our next question is, by analyzing the graph, does this appear to be an increasing or decreasing function? And does there appear to be a positive or negative correlation? If we look from left to right, we can see that the number of equal pairs are increasing. So this will be an increasing function. And it's also looks like if we were to draw a line through this, we would see a positive correlation, meaning that it's going up. So that matches the fact that it's an increasing function. So to determine which function best represents the model in this situation, a linear, a quadratic, or an exponential. So let's try that for each. So for a quadratic function, let's start with the linear. So y1, grab your tilde, and that's under ABC, tilde, mx1 plus b. So if we look at the linear function, we have an R value of 0.9061, which does have a relatively strong correlation, but the R squared value is 0.821, which means 82.1% of the data fits the model. So let's see if the quadratic is a little bit better. So quadratic, y1, grab your tilde, and then ax1, we need to square it, plus bx plus c. bx1, rather. There we go. So the quadratic model is interesting, but let's just retype that. Disappeared. ax1 squared plus bx1 plus c. So the quadratic model is interesting, but we can't really make an argument for the quadratic model since we don't know anything about what happened before 1960. We don't know any of the data before 1960, even though this does appear to be an even stronger model than the linear. So let's take a look at the exponential model. So exponential model, y1, grab your tilde, A, parentheses B, and we need to raise it to an exponent, x1. So the exponential model has a 95% R squared value, which is a little bit lower than the quadratic model, but we don't know anything about what happened before 1960. So we're going to argue that the quadratic model or the exponential model is the best fit in this situation. We'll stop and we'll go back to answering our questions without using the graph. All right, now we're ready to answer using the table, graph, or function, identify the domain and range. So let's write down domain. We'll use D. So we're just going to use the table. So our smallest x value, which is our domain, will be 1963. And then our highest x value will be 2006. For our range, we'll use R. Our lowest x value is 487. And our highest y value will be 9789. And that covers our domain and range. Now, when we looked at the graph, it says draw a smooth curve over the data points using the function you chose to show a strong or weak correlation. So that did show a strong correlation when we looked at the graph, because a lot of the points did hit the graph. And also we saw the R squared value was really high. Using the function you found in part 5, determine the bald eagle population in 2015, 2020, 2025, 2030, 2040, 2050. So let's go back to Desmos and answer that question. Okay, now we can answer that question. We're just going to have to type in our functions. So first, we're just going to say y equals 1.02 02 times 10 to the negative 55th parentheses 1.07002, and we're going to raise it to an x. So there's our y function. Actually, let's call it f of x. Okay, since we wrote this as a function, we can just type in f of 2015. So f of 2015, this tells us how many nesting pairs there are in 2015. So based on this model, it would be 17,114 miles in 2015. The next model we want to know is 2020. So based on this model, in 2020, there should be roughly 24,005 pairs in the lower 48 states. F of 2025 is the next one we're being asked to find. And based on this model, it should be around 33,672 nesting pairs in the lower 48 states. Next we want to know about is 2030. So in 2030, we should be roughly 47,231. And we want to know about 2040 and 2050. So F of 2040, we should be at 92,929. So get close to what we're at around the Founding Fathers' time. But is this realistic? And then if we look at the model in 2050, we should be at close to 200,000 at 182,839. Question 9 is asking, do you think you could use this function to predict the bald eagle population for several years after 2050? And no, because this is gross extrapolation. It's too far outside the data set. Really, anything after 2006 is too far outside the data set. So too far from data set. And then using the function you found in question 5, determine when the bald eagle population will hit 100,000 nesting pairs of bald eagle like that of 1782. So let's try to answer this question using Desmos. In Desmos, what we want to do is we want to type in y equals 100,000. And we can't quite see 100,000, so we're going to have to zoom out just a little bit so we can find it. There we go. Here's our 100,000. So that looks like it's in 2041, 2042. So that based on this model in 2042, we should have reached 100,000 nesting pairs like that of 1782. Hopefully this helps you understand how to answer questions based on models and finding a model if you don't know what type of model you're looking for.